Okay, so up to this point, we've gone and done some of the different applications that you can, do using the ideal gas law. Dealt with gas density, we dealt with molecular weight, and being able to determine the value for both of those, using the ideal gas law. Today, though, we're going to go over gas stoichiometry, which, yes, stoichiometry is in the name, so it means we are going to be dealing with grams and moles, and that type of thing. Now, basically, I like to describe it as stoichiometry meets the ideal gas law, where you're going to be using both concepts to be able to figure out these problems. Nothing really new to learn. You already know how to do stoichiometry. You already know how to use the ideal gas law. So now it's just basically bringing the two together. You can solve the problems using knowledge you already obtained. Like I just said. One thing that you do have to make sure that you pay close attention to is just that whatever information that you're given, you need to determine exactly what substance that is that you're given, and also what substance it is that you're actually looking for. By doing that, you'll be able to better understand this, I believe. You know, as you know, with a regular ideal gas law equation or a regular gas law problem, I mean, you're given information for just one substance, so whether it be, like, let's say nitrogen gas or oxygen gas, something like that. It's just for one substance. You don't have to worry about anything else. With stoichiometry, though, you actually have multiple substances that you have to deal with, where some of the information that you want to use is for one substance, some of the other information that you want to use is for another substance. So you do have to take those two things into account. But probably the best way to explain this is just to show you an example of it. So this example is in your note packet, and we'll just go through it now. So it's just basically asking you for the how many grams of NaN3 do you have or would be required to provide 75 liters of nitrogen gas, 25 degrees Celsius at 748 millimeters of mercury. So as you can see, you're looking for grams. You already have volume, you already have temperature, you already have pressure. And here is your overall equation, which anytime you see an equation, you should know automatically you're doing a gas stoichiometry type of problem, because this is the only type of problem that has that. Now, as you might notice, again, as we were reading through this, you're looking for the grams of NaN3. So you're looking for the grams NaN3, but the problem is you have 75 liters of nitrogen gas, the 25 degrees Celsius deals with the nitrogen gas, and the 748 millimeters of mercury deals with the nitrogen gas. So you have two different substances here that you have to take into consideration before you can actually do this problem. Now, probably the easiest way to do this is that, since you have a volume, a temperature, and a pressure, why not use the ideal gas law? And what you can do is just solve for N, or solve for the number of moles. That number of moles will be the moles of nitrogen gas. Then from there, using the knowledge that you have for stoichiometry, you can figure out the grams of NaN3. And let me show you that right now. So here's the problem. First off, I just went and plugged it into PV equals nRT. So you have, your pressure 748, just make sure it's in atmospheres. You have the volume 75, and you're looking for R's are always 0.0821, and then temperature you have 25 plus 273 so that you get Kelvin. Plug that into the PV equals nRT equation, solve for it, and you end up with 3.02 moles, and again that's for N2 because that's what all that information was for the N2. Now, using stoichiometry, though, you can easily get to NaN3. So in this case, you have 3.02 times, this is just the mole ratio, and if we go back to the previous slide, the 6 that you saw on the other slide, the 6 is that, it's the mole of the unknown over the 9, which is the mole of the known. So it's 6 over 9 for the mole ratio. Multiply that by the 3.02. That's just the molar mass of NaN3. Once you do all that out, you end up with the mass for NaN3. So it's 131 grams. Again, nothing really new here. You already know how to do stoichiometry. You already know how to use the PV equals nRT equation. It's just basically making sure that you read through the problem and you know what it is that you're given, what it is that you're looking for, and then that way it'll make it a lot easier for you. different type of problem that you might have. And again, this is in your note packet. This case, you're actually looking for the liters of chlorine gas. You have 40, it's at 40 degrees Celsius, and you have a pressure of 787 millimeters of mercury. And you also have the gram amount for HCl. Now the problem in this case is you're looking for the liters of chlorine gas, and everything dealing with, liters or anything dealing with the ideal gas law is going to deal with chlorine gas. So for instance, the 40 degrees Celsius and the 787 millimeters of mercury, that's all for the chlorine gas. So you can't use that along with this in the PV equals nRT equation. You have to do something first. So if we come over to the next slide, basically what you need to do is first change that gram amount over to moles. So it's just 9.41. I just changed, I divided that by the molar mass HCl, which is 36.46. So you get that number of moles. Problem is that's the moles HCl. Like I was saying or trying to say before, you need the moles for Cl2 because that's what all the rest of the information is for, for that Cl2. So you have to multiply by the mole ratio, which, just to go back, in this case, you're looking for chlorine, so here's your 5, and you have HCl, so here's your 16. So that would be the ratio, 5 over 16. So take the number of moles of HCl, multiply by the 516, you get the moles of Cl2 in this case because of the fact that you use that mole ratio. Now, because you have the moles of Cl2, you can plug it into PV equals nRT because everything now matches up. So for instance, you have 787 millimeters of mercury, change that over to atmospheres, volume you're looking for, N, you have it, so 0.0807 moles of Cl2. You have the R, temperature was 40 degrees, make sure you add 273 so that you have 313 Kelvin. Then just plug it into PV equals nRT and solve for V, which in this case is 1.99 liters. So that's it for gas stoichiometry. Again, you already know how to do both. You already know how to do the ideal gas law. You already know how to do stoichiometry. So now it's just meshing both of the things together. But again, make sure you are careful to determine, what substance each of the values or each of the numbers are for. If you have any gas, anything, and let me just go back to the last slide. Any gas, anything like the 782 millimeters of mercury, 40 degrees Celsius, that basically goes all together, so with the liters of chlorine gas. So all this deals with chlorine gas. So that means you have to deal with that separately, that type of thing. So now just work on, the worksheet that I passed out to you. And tomorrow we'll go over partial pressure, which is the last application, and just a reminder that you do have a test coming up next Monday, February 6th.